Today, I'm going to show you how to calculate the closest obstacle to a laser scan, provided that this laser is moving in some way. Maybe it is moving like in this system that I can show you here on the screen. That is, the laser is rotating in itself, but maybe the laser is mounted into a robot and this robot is moving in some direction. So I'm going to show you how you can calculate at any point in time what is the closest obstacle to the whole system and how to refer this closest obstacle to the base link of the robot. So here we have the simulation for showing how to do it, and we have this rotating laser mounted on a tripod, and let me show you here where it is located into this environment. It's just a gas store. Okay, so the robot is there. Great. And how does it look in RBIS? So in RBIS it looks like this. We have two links, the base link and the laser link. All the measurements of the laser are provided in the laser link, of course, but then we want to modify those measures and put them reference into the base link, so we can know at any point in time from this center, the center of the robot, which one is the closest obstacle. For that, let me show you, if I move away from here, let me show you what I have prepared. Here you can see on red the laser scan of the robot, of the laser, sorry, that is showing what the laser is detecting on the simulation here. Yes, based on the structure where it is put. And then I have created a program that it is what I'm going to show you, that points a yellow dot to the closest obstacle to the robot, to the base link of the robot. So you can see how this yellow point is moving from there to there, depending at which point in time the closest obstacle is on one location or it is on another. Okay, so let's see how we can do this. And for that, let's go to the ROS Development Studio, where I have prepared this, and the system that you can access at any point in time and do your demos like this one, your programs for robot. It's at rds.theconstructsim.com. Great. So here I have the simulation that is rotating there, and here it is a program that I have created. So for that I have created a package that I have put it into our CAD-CAM workspace, of course, and it's here, the closest obstacle. Okay, source code. So I have created this, and this is exactly the program. So let me put a bigger screen, and maybe we can increase the size of the, yes, let's put 18. You can see better now. So what are we doing? I have created a laser class, and what it does, this class, first it subscribes to the scan, of course, to the laser, and it calls this callback for the subscription. Okay, and the callback, the only thing that it does is just to store the value of the laser that we have received. Then what also we have the publisher. The publisher is the topic in which we are going to publish the position of the closest obstacle to the robot. So by publishing this as a pointer stamped message, we can show the message here on RBIS. Okay, so this is the first two things that we are doing. The next thing is that we are going to use TF in order to provide the transformation from one frame, the frame of the laser, to the other frame, the base link frame, the center of the robot. Okay, for that we need to use those two functions from TF, and of course we have to import TF to ROS and TF to geometry messages. Then having done that, then the first thing that we do is we create a buffer of TF by calling this function. And we provide the length of the buffer. It means the duration in time of TF transforms that we are going to keep in our buffer. And then we create a TF listener. The TF transform listener is the one that will create afterwards the transformation. Okay, but first we have to create this object in order to use it later. So we have created, and then finally we call for the first transformation. This is in the initialization of the class. Okay, so this first transformation is the function that will transform actually. So in this case, we are creating the transform by calling this function lookup transform. And in this function, this is the one that provides the transformation between the laser link and the base link. Okay, so this is only computing what is the transformation at that point in time between the base link and the laser link. So you have to be reminded that we have to call this all the time because the laser link is moving, as you can see here. So it's not possible to get the transformation, a single transformation at the beginning of the program, and that's all. And so we have it, and then we use it to transform the points. It's not like that. So we have to be calling this function repeatedly as we get new laser data in order to see to change the transformation depending on where the laser is at that point in time. Okay, so this is during the initialization. We get the first transform and we check that is correct. Great, so we have this initialization. Then on the callback of the laser, the only thing that we are doing is to get the message of the laser, the whole message, and also get the transform at that point in time. So at that point in time, we are calling to this function again and get the transform at the same moment as we have received the message. And why at that moment? Because at that moment, we know that the laser is at the proper position at which this message was generated. So that is why we have to call this function at that point. Otherwise, if we wait until we call again the transformation, then we'll get a transformation that is not valid, that is not equivalent for the message laser that we have obtained. Then finally, we have created here a publish function that is the one that is going to publish this topic is going to publish the position of the closest obstacle. And how do we do that? Very simple. We get the laser ranges, that the latest laser values that we have stored here in the callback. So we get it, and we only focus on the ranges, and then we check which one of these ranges is the closest point. So it's just a typical for, you know how to do that. Then we look for the shortest laser in this loop. And the only thing that it's a little bit different is that we are going to discard this is for our case, okay? Because here in the simulation, as you can see, the robot, the laser is detecting all the time the ground. So we want to filter those values because they make no sense. So I know that there is the ground here, so I'm not looking for that. What I am looking is for the other obstacles that are around the robot. So for that case, I have implemented here a short function that allow me to change, to discard all those values that are related to the ground detection of the laser. Okay, so at that point in time, after this for, I have here in this point, I have the x coordinate of the closest value and the y coordinate of the closest obstacle. So I have in point x and point y, I have the closest obstacle to the robot. Great. Then in order to make the transformation, I'm going to call a function that is called do transform pose, and for that we need to provide a pose. And then in this case, so I'm going to create here a pose, then fill it with the header of the laser so it has the same time, and then provide the position, the proper position of the closest obstacle. For that, in point here we have the x and the y, And then we only have to provide the Z that is 0 and Y is 0 because the obstacle is measuring only in the X and Y axis, the red and the green, and not on the Z. So we know for sure that any point measured by the laser is on Z0. That is why we assign 0 here directly. And then the rest of the coordinates have been calculated in this loop. Okay, so in point we have the exact location in X, Y, and Z of the obstacle. Then we provide that value to the pose, and we provide this pose to the function do transform pose here. And also, of course, we had to provide a transformation. This transformation is the one that we have compiled, that we have obtained here when the laser was obtained through the callback. You remember? So when this laser callback was activated, we got the ranges, and we call the get transform function that obtained this self transform that we are using here. Okay, so once we call this function do transform pose, we get here the pose transformed, and then from there I only have to retrieve the point that is stored into the pose transform pose position. I retrieve this point, and then I just publish on the topic, and that's all. Then this position of the closest obstacle will be published in a topic, and if it is published in a topic, then we can watch it through RBase, of course, as a pose transform, as a point transformed. As a point transform, point is stamped, so it requires to have the time on it. That's it. So the rest of the thing, this is for the class, this laser rod class that I have created, and then the rest of the thing, just the initialization of the node, the rate at which we are going to call the function of publishing closest obstacle, and then the instantiation of the class. We put this inside a while loop, and we call at this rate of 10 Hertz, we call it the publish closest obstacle. That's it. That is this function that is going to get everything. So this here in the RBase, we can see the result. As you can see, sometimes the closest obstacle is on the, of course, is on the verge of the lateral of the laser, and when the laser rotates in an area that is very open here, as you can see, there are some open areas around here. Then when the laser is detecting those open areas, the closest obstacle is on the top, is on the ceiling, you know, it's here. And when the robot is rotating and detecting those areas, then it points the closest obstacles to those obstacles here, as you can see here. So basically, that's it. So I hope that you enjoyed this video and that you understood how it works. So you can pause in the different points in case that you want to get the program and how it works. And in case that you like these kind of videos, please subscribe to our channel and press the bell so you will be notified every time that we publish a new video. Remember that we are publishing these kind of videos with practical answering questions, one every day, and with many tutorials for learning many other subjects of ROS. So thank you very much for being here and attending this video, and see you next week.